All right. So as we talked in the last lecture, we started about memory hierarchy, right? So we talked about cache, and we started to define the first, second, and third classes of caches. So we thought about direct map caches. Let me just bring it back. There must be a slide with. So we talked about this. We talked about different classes of caches. All right. So the first one, which we called it direct map. You can see it here on the left side, right? So we talked about this, that okay, the data in cache, the location of memory blocks, okay, in direct map cache, there's only one way to map that, all right? And we just use a mod for the data, for the number of block, okay, in order to find the specific block in a cache. That's why the block number is always would be the same given your data here, all right? So for instance, here your block of data is 12 mod. How many blocks here we have in our cache? It has 8, 0 to 7, right? So if you just do a 12 mod 8, what you're gonna have is gonna be 4, right? It's the remainder of 12 out of 8. And it will show the block number of the data in the cache, right? And we call it a direct map because this data is directly mapped on this block of the cache. So if you're looking, if the memory address corresponding to this block of data comes and you search this block for and you didn't find it, definitely it's going to be cache miss, right? And we talk about cache misses and cache hits. If you find the data, that means you had a hit. If you didn't find it, you have to come back one level lower in your hierarchy. If you're in L1, you might go to L2 or L3, or you're going to go to your memory. Or if you had only one level of cache, from cache, you have to look back to your memory and fetch the data using the address and bring it back up. So that's why you have a miss. And you have to pay a penalty because you search once your cache, you didn't find it, now you have to go back and search in your memory and then bring it back up. And normally the lower level cache, in this case the memory, is much slower than your cache, right? So you prefer to hit, but even with 5% cache miss rates, you have to pay a huge price in order to come find it, all right? So that was the first direct map. The second class, the second and third are sort of in the same family because they're dealing with associativity, right? So this is one side of this spectrum. Exactly on the opposite side, where you can find this anywhere in your cache, right? It's called fully associative. That's why if we are trying to find the specific block in cache for that data, we need multiple, right, hardware searchers in order to come find that specific inside a cache. Remember, for the direct map, you only had one choice. Because of this, it would be only mapped to block 4. In a fully associative, it's going to be mapped anywhere, right? So somewhere between these, there was a question?
I have a question.
Yeah.
Yeah, so for the fully associative, we can't use the mod formula, right? Because it can be put anywhere.
Yeah, it can be placed anywhere in those blocks. Still the same data, it's still the same size, right? You still have 8 blocks in this example. Yeah. But they can be everywhere, anywhere on those 8 blocks. So somewhere in the middle of these two, right? So I'm just gonna put it any here. So and this is just only, right? So somewhere between this any and only, you have set associative, which is depending on the set number of sets, right? Which defines the number of sets per associativity, and hence the name set associative. You might find it with n, right? Two-way associative, four-way associative, and so on and so forth. So you might find certain sets of blocks, right, that you have to search into. Now, you see that the search hardware here has been shrunk because of having this number of sets, right? In a two-way set associative, right, we have two-way set associative. That's why we have 0, 1, 2, and 3, right? There would be 4 sets because we had 8 blocks, right? And this memory block 12, which could be placed anywhere in the fully set associative, now we need to only find it in this set 0. Why? Because 12, now instead of mod all of the blocks, right, what we should use for the mod is the number of sets we have. A two-way set associative has 4 sets, right? So the result of this would be 0, right?
Mm-hmm.
So this data could be only found in the set 0, which has 2 blocks here, all right? So that's why we need 2 hardware searchers, okay, comparators, to search and find the data, all right? Any questions?
Yeah, so you said it's in the 0 set. So how do we know it's in the first half or second half?
So there is another one. There is another metric called tag. We're going to talk about it. Also, tag will be used for direct map as well. So using tag, you can understand which of those you're going to search for. Also for the direct map. So this is a much longer size, right? You recall here. Let me go back to the first one here. So this is a direct map cache, right? All of these grays are going to map to this block 001, right? You see, it's not only a singular gray, but we have multiple of those depending on this size. And recall, I was talking about the case that in this case, because we have only 8 cache, right? So 3 digits would be enough to distinguish all these 8, right? This must be matched to the last 3 digits of this address, right? All of those grays, if you take a look, they have 001 at the end. That's why you're going to see all of them are going to be mapped directly to the block 001. How are we going to distinguish which of these? We're going to use tag. And we have examples today we'll talk about, right? Another example would be these blues. All the blues will be mapped to 101. And if you take a look at their address, all of them finishes with 101, all right? The last 3 contains 101, all right? 101, 101, 101. And the first 2 is actually the tag here. We will talk about examples. Okay, let's go back to where we were. Any questions?
Yeah, so we stopped on slide 51.
Yeah. All right. So we talked about the advantages and disadvantages of having all those 3 different caches, right? For instance, in one of the benchmarks that is very well known called Spec 2000, so they have run a test, a simulation of the same size cache, 64 kilobyte of Dcache, right? And 16 word block. So each block has 16 word size, right? And they've used 4 different caches: 1-way, 2-way, 4-way, and 8-way. Okay, and on average, they found that okay, so 1-way set associative, which is in essence, what is it? When you have a 1-way set associative,
Direct map. It's a direct map.
Any other idea?
misread.
What? Yeah, actually, your friend was right. I'm just trying to see if you have other ideas. So one-way set associative, if you look at this, you have only for each of the set, you have one way, right? So we're gonna call it a direct map. Here we had eight blocks, right? So we can distribute it either one-way set associative, right? Or a two-way set associative. So each of those can be placed in the sets 0, 1, 2, and 3 because you have two-way sets. So you can have four of these sets. Four-way set associative is each of those tag data are going to be placed in one of those, right? 0 or 1. You have 4 options now, okay? And 8-way set associative is you have only one giant block of cache, and then it can go anywhere, right? Your tag data could be gone everywhere. That's why you have 8-way, because you have 8 pairs of these tag data, right? There's 1, 2, 3, 4, 5, 6, 7, 8. Okay, this is the 8th one. So this tag data could be placed anywhere. That's why we call it 8-way set associative. So people have ran tests and they found that it's going to help sometimes when you have a fully set associative. You might be able to reduce the cache misses on average, but then on the downside, you're using more hardware for that, all right? So let's have an example. I was talking about the fact that every instructions, if you want to load a block in an associative cache, you need to come up with these 3 numbers. So values, tag, index, block, offset, all right? Let's see how we're going to define this. So for index, we're going to use this index in order to select the set. If you recall, for instance, on that two-way set associative, we had 4 sets, right? So for instance, for a two-way set associative, you have 4 sets. Set 0, 1, 2, and 3. How are we going to distinguish about these 4? We're going to use index from the incoming address. Tag. We're going to use tag to choose the block by comparison with the blocks in a selected set. You're going to see an example in 2 slides, and it's going to be pretty easy actually. It's one of the easiest examples you can have, and in your final test as well. And the block offset is actually the address of the desired block. So your desired data in the block has a block offset. So normally when you are given an instruction, I don't know, in 16, 32, 64, you need to find each of these segments, and using those segments, you're going to come up with the size of the cache and see how you're going to map it in a cache, right? This is the high-level view of a 4-way set associative. So that's why you have a 4-to-1 multiplexer here, okay? So 4 comparators are needed here, and that was your address, okay? So we need a 4-to-1 multiplexer to choose among the 4 potential members of these selected sets, right? Either of these 4. And the cache access, it consists of, right, indexing the appropriate set, because we need to. So this portion is going to give us the index. This portion out of this 32, 8 is going to give us the index. 22 is going to give us the tag, and this 0 and 1 was actually the offset. All right. So the comparators here, when they're coming down, they're going to decide which element of the selected set matches the tag. Okay. So for instance, this index of 8 is coming here, so you're at this, and then you're gonna decide, the comparators will decide, right? Because 1 out of 4 would be the final answer, right? That which of those elements of the selected set matches the tag, all right? And the output of the comparator will be decoded in a signal. So let's have an example here. Oh, also, I remember I talked about the least recently used method in order to choose the unused longest time. Does anyone recall what it was?
Yeah, I remember.
So can you give us a quick definition?
Definition? I don't really remember, like, know the definition, but basically in slide 50, when we were setting the memory, when we were getting, yeah. So in that slide, for example, the last line, for example, we changed the M0 to M6, for the memory 0 to memory 8, because memory 0 was the least recently used.
Right.
So the next one was, it had memory 8, which is the new memory, the new data from the memory, and the previously one, which is the memory 6. Memory 0 was ignored because it was least recently used.
Right. That's right. That's right. Yeah. Everyone got the idea? I mean, we talked about it last lecture. If you weren't attending the last lecture, you can always feel free to go back to the videos.
Professor, I have a question.
Yeah.
So on slide 53,
okay.
So I know what the index is, but what is the tag?
The tag actually is the remaining. So the remaining so just think about a mechanism that you want to find some blocks of cache using an address. Okay. That's all that matters. So depending on how you play around with this tag, index, and offset, you want to play around with the different cache architectures. All right.
Basically,
so,
tag and index concatenated by each other makes an address, and that address is what we are looking for.
Yes. Yeah. So when for instance you're asked how many bits are needed for the tag, and you started from the huge chunk of, for instance, 32. If you found out that okay, you had 0 and 1 here, is this bit for the offset, and then you had needed 8 bits for index, so you can just add these two up and then deduct it from 32, so the result will be 22 for tags. Okay, this is one way to come up with the size of the tag, which you'll see in an example right now. For instance, let's just wrap this one, because before we start the question, for the replacement policy, we're gonna use it only, right, when we have n-way set associative. Because in direct map, we have no choice. We have only one choice to use, right? It's a directly map, so there is no replacement policy. On the set associative, normally what we use is a least recently used, right? LRU, and choose the one that has been unused for a long time, because we might think that, okay, the next iteration, the next access of the memory, we might not use it anymore. Again, going back to the spatial locality, remember when I was talking about those convention that, for instance, when you're in a loop, some of those adjacent or contiguous to your iterator, like if you are having an array of I, and I as in its 12th element, right? It makes sense, might be the case that the algorithm might use 13, 12, or 10, somewhere close to 10 and 12, which was the iterator, right? So if you had one from iteration number 2, right, it might make sense that because of this least recently used policy, you might want to avoid using it. You might just want to replace it with the one that is more recent. The other policy would be just to place it randomly, either of the cases, right? Just randomly select one of them. So these are different things that has been implemented in real world architectures. But here, most of the cases, we're going to, in a question statement, you're going to see the policy, so you have an idea how to proceed with that, all right? So let's have a question. Before we start the question, do you have any concern or other questions? Let me see the chat. Okay, now you're gonna see. Okay, with this question, you're gonna see all of them. All right, Joey. Shall I start? Okay. So the question is, well, I think somebody's knocking my door. Let me see. I'll be back, guys.
Yo, how's everyone? Someone turn on the mic, guys. Don't keep talking to yourself. Abu Rajhi. Yo, guys, is anyone talking?
Hello, hello.
How are you guys?
Chillin'. Wait, how can I see you guys? I can't see anyone.
Can you guys hear me?
Yeah, we can hear you, bro.
Yo, where's the prof?
I like his profile picture.
Somebody
He's
was
answering the
knocking
door.
Oh,
Wait, so did he talk about changing the weighting of the labs?
No.
Yeah.
All right, enough with fun.
Are you
I'm back.
okay?
That was faster.
Yeah, the last thing you want to have in pandemic is someone knocking your door.
Yeah.
All right, so the question was, assuming a cache of 4,096 blocks, right, a 4-word block size. Okay, now the overall block number is 4,096. All right, each word, each block has 4-word size. Okay, and a 60-bit address. So the address overall has the length of 60-bit address. So now the question is, find the total number of sets and the total number of tag bits for cache. For all those three, direct map, two-way, and four-way set associative. Well, actually, we have been asked to just have it for two-way and four-way, and also a fully associative. All right. So let's see how we're going to tackle this. So there are 16. The question said they are 4-word block size, right? 4,096 blocks and a 64-bit address. All right. So what we're going to have is we're going to have 4-word block size. So each of those word block size is going to be overall, when we have 4 of them, because each of them is going to be raised to 2, so we're going to have 2 to the raise of 4 or 16 bytes per block. Okay, so overall we had 64-bit address, so we need to use 4 bit of those address in order to use for that block size or the offset, right? We have to address 16 blocks, a 4-word block per size, right? So we need to have 2 to the raise of 4, and we're going to reduce that from the number 64. That will give us 60 remaining. All right, for both tag and index. So we've already figured out this portion of that, okay, which was 4. Overall was 64. So this portion comes up total 60. Okay, is that clear so far?
I have a question. So to find the bytes per block, if the question says we have a specific word block, I just put 2 to the power of the number of the word block that I have.
Yeah, I'd say don't try to memorize this, because the wording might mean different things, right? Like word per block size or word block size. So if you just memorize and just raise it to that number, you might just have a
Okay,
error.
so I don't understand why did we find 16 and why did we deduct 4, and what is the 4 that we have deducted?
So by having 4 bits, you can represent 16 bytes per block.
Okay.
Right? You need 4 bits in order to represent 16 number in a binary word, right?
Because we have 4 bits in every byte, or no?
No, every byte has 8.
8.
It's an 8-bit byte.
Okay.
Right? Does that make sense?
Yeah, kind of. Let's see, maybe it will be more clear.
Okay, let's carry on. So for now, we understood that, okay, we need 4-bit for those. Now 60-bit remain for index and tag, right? So let's see, depending on the architecture, let's see how we're gonna deal with distributing that 60-bit to address those, okay? Let's go with the direct map. So direct map, overall, we had what? We had 4,096 because of the question. We had 4,096 blocks, right? So in order to address 4,096 blocks, okay, how many bits we want? The opposite method of getting an exponential is by getting a log 2, right? Because a log 2 of 16 is going to be 4 again. A log 2 of 4,096 will give us 12. And you can easily, you don't even need a calculator for this. If you always recall 1,024 is 2 to the raise of 10, right? From that point on, you can just multiply it by 2 or divide it by 2, and you're going to come up with numbers pretty easy. Always remember 10,024 is 2 to the raise of 10, okay? So 4,096 is 4 times 10,024. So you need 2 more bits, right? Because 2 to the raise of 11 would be 2,048, and 2 to the raise of 12 would be 4,096, right? This will help you just to come up with numbers very fast. And since we are talking about binary word, you might see these numbers quite often, and you don't even need a calculator for that. So a direct map, we need to use all of those, okay, for index. So how many bits we want? It's going to be 12 bits because we want to address 4,096. So the total number from that 60 remaining bits would be what? 16 minus 12, right? And we need to multiply that to the number of blocks because we want to come up with the final size, okay? So 48 left to be assigned for 4,096 blocks. So overall, what's going to be the size of that direct map is going to be 197K tag bits, all right? Is that clear?
K as in 1,000, right?
Yeah, K as 1,000, yeah.
So, Professor, this question is asked for the tag bits. How about if the question asks for the index bits? So we just need to use 12 times 4,096.
Yeah, exactly. Yeah. I mean, you just have to represent what the question asks you by the amount of the metric they were interested in. In this case, was tag bits. So each tag per bits, right? Or each tag bits as a pair, right?
I don't exactly understand what does the index mean. Like how the index represent what.
So index actually helped you. So in a fully associative, index is pretty easy because you. Oh, let me just bring back to the first example you're gonna see here. Remember this tag data, right? You had index here, right? Did you recall?
Yeah.
Index is actually indexing the block for you.
Oh, so it's index which block I should go into.
Yeah, but we use tag in order to understand if the data, if each of those, so we have 2 things now. So we use index in order to find if the grays, all the grays are going to be mapped to gray, right? But when we are here, we have to find which of these grays were here. And thus, we need to use tag, okay? Because all of the indexes are the same, 001, right? The last 3 are 001. But when you're here, you have to understand, okay, oh, which of these came here, directly mapped here, and then you're going to use their first 2, which was the tag here. 00 in this case, 01 in this case, 10
So
and 11.
the first 2 actually here is the tag.
Right.
Okay.
Yeah, as you see in this example, so we have, so this binary address came, so the first two for the tag, and then the last three in this specific example was for index. And this number in binary represents 22 in decimal, right? Just like that. So now, just like this, now we have, instead of 5, we have a 64-bit now, a pretty larger, in a real world application, yeah, in RISC-V and many modern domain, you might have a 64-bit or 128 or 32, right? So now we are, instead of allocating 3 now, we are allocating, what was that, 12, okay? And you found it using a log of the overall 4096, right? Here. So we had 4096 blocks, a 4-word block size, and a 64-bit address. So you figured, because of the block size, for a 4-word block size, we're going to use 16 bytes per block, okay? And each byte is 8-bit byte, right? Each byte is 8-bit. So by allocating 4 bits, you're going to address those 16 bytes per bit. So that will leave you with 60, and then you add 4096 block. So a log of that would be 12. So the remaining would be 48, okay? And then you multiply that to find the tags. So that was a direct map. Now let's go one step further. After that, you're going to have a two-way, right, set associative. Now instead of a direct map, we have two-way set that will lead us with multiple sets, right? Now, a two-way set will reduce what you found in a direct map by a factor of 2, right? Because each of those could be placed in either of the sets. Recall again here, a direct map that was directly mapped here, but in this, which was actually a two-way set, you had 2, right, options per each of the sets, then you have multiple sets, right? So now, in order to address these changes as well, now we have to take one more bit in order to address the sets, okay? Right? It will reduce what we found in the direct map by a factor of 2 now. So we will take one more bit from it, okay? And when you take one more bit from this, it's going to be, instead of 4096, you take one bit out of it, which is 11, right? Instead of 12, it's going to be 2048, okay? So the total tag bit is going to be, instead of 60 minus 12, it's going to be 60 minus 11, right? Two-way set, you multiply it by 2 of those 2048, which is the same as 496 above, right? So what changed was the fact that now you're, instead of multiplying 48 by 4096, you are multiplying 98. Yeah, I'm sorry, this is 49, right? Because 60 minus 11 is 49. Now 49 by 4096, and that would increase the tag bit size, okay? And this is understandable because your tag bit will be increased. You have more options now. You can put one step further. Instead of two-way set, now we're gonna have a four-way set, all right? Now, it's a four-way set. Now we have to reduce the block number by a factor of 4, right? How many bits we want to represent 4 in binary? 2 bits, right? 0, 0, 0, 1, 1, 0, 1, 1. So 2 bits will represent this factor of 4 for us. 0, 0 up to 1, 1. So from that 60, instead of taking 12 for direct map, instead of taking 11 for two-way set, now we need to take 10, right? And what will remain is 1024 sets. right? Because you have four-way set associative. Now, if you now multiply this, it's going to be 50 multiply again 4096, which is 205 kilobits, right? So this 4 multiply 1024 would be the same as 4096, or 2 multiply 2008, right? What changes here is the amount of bit that we are taking and we're exchanging between index and tags, okay? And finally, a fully set associative, there's only one set, right, with the whole 4096 of blocks, and the tag size is 60-bit, right? So you don't have to reduce anything from it. There's no blocking here. There's only one. So leading to a 60 multiply 4096 and 1, which is the whole giant block of cache, and that would result in 246 kilo tag bits. All right? Any questions? I'm seeing
Yes.
8 in chat.
Yeah, go first if you want.
Yes. I want to ask: is the tag bits larger is better or smaller is better?
It's a trade-off. You see here, different systems are using different methods, right? So, for instance, a simulation on a 64 kilobit and 16 word block size on a SPEC 2000 benchmark, it contains several benchmarks. The result was using it one way would, on average, give you 10% miss rate, and an 8-way was giving you a little bit lower, okay, a direct map versus the fully associative. So there are somewhere between here. The actual recent cache systems are normally around this 2 or 4, okay, somewhere around here. But this is a trade-off, right? Depending on the scenario, depending on the code you're running, and depending on the way you are using your spatial and locality, right, or your cache. So you're gonna have different cache misses. It varies. Okay. Other questions?
Sir, I have a question. So for this two-way, four-way, sorry if I'm being repetitive, two-way, four-way, so it's always -1, right? Because we started with 12, then we did -1.
No, because we started from a direct map. If we have started from this, that would be the reverse, like, right?
Oh, so you would add it.
Yeah, because just this is another example of that figure that I show you here. Here, we started from here, a direct map, which is effectively a one-way set associative, right? We have only one-way set.
Yes.
There's no set, actually. There's only blocks, okay, tag data, and that validity bit that you saw. So you have 8 blocks, tag data, right? And each of them has only one way to set that, either in 2 or 3 or 4. So it's a direct map. Then you put one step further. You make the one-way set associative as a two-way set associative. So for each of those, you have 2 options set, right?
Yeah.
It could be in any of those, 0 and 1 on each of the cases. And then you go one step further, and then the more you go higher with the n-way, this n number, your number of blocks, right, needs to be reduced because you have now multiple options.
Yeah.
Now you have 4-way set associative, right? Here you had to have 2 comparators, right? One here, one here. Now you need to have 4 comparators. Tag data, right? Now this is your fully associative. Now you need to have 8 of those, right? So now we started from this and we gradually move down towards this. So when your overall addressing is 64, in order to address a fully set associative, you just have to remove that 4-bit and then use the rest right away, because there's only one set.
Okay, thank you.
So the fully set don't have the index.
Yeah, yeah. I mean, it's one index. It has like one.
Oh, okay.
Professor, I have a question. So the 60, we
Oh.
got it by doing the bit address minus the word block size.
The 60, yeah. So it was 64 minus 4.
So is this always the case that it's the
No,
address?
because the question asked us, right? The question asked us if so a 4-word block size.
No, I mean it's always the address minus the block size.
Yeah, because this is your overall address, right? You have this length of addressing in your, and always your memory addressing should match your cache.
Mm-hmm.
And that's why I thought I told you guys, when you buy a CPU, when you want to increase your RAM, right? That speed of the RAM, that size of that length of the RAM, the technology like DDR3, 4, 5 should match what your CPU is capable of. Otherwise, you're gonna have mismatch of addresses, and your computer won't even boot. Okay, because for instance, if it has like 32-bit addressing and the other one is like 64, or their speed is different, there's no way your computer even boot.
Mm-hmm.
So if it's 64, everything in that system is running on 64-bit because the addressing should match. You're gonna run those instructions, and you have to find the addresses in either memory and then or your hierarchy of memory, right? So you had 64-bit, you excluded that 4-bit to address a 4-word block size. So 60 remained, and depending on the architecture of the cache, you are distributing all of the 60 or 50 of those, 48, 49, depending on the case. All right?
Okay, and just to understand the structure of this question, for the two-way set and for the four-way set, I multiply the two-way set by 2 after deducting 1 bit, and then I multiply by 4 after I deduct 2 bits. If I'm starting from that.
Yeah, the only difference between, yeah, depending on the n here, right?
Mm-hmm.
You need to take some bits, right, in order to address those n. If n is 2, you need to take 1 bit. If n is 16, you have to take 4 bit, right? If it was allowing you. If
Okay.
it's 4, you need to take 2 bit because you have to address those 4, right?
Yeah, and where do I get the number 2048? So I understand if I did log 2 2048, I would get 11. But in this case, how did I know it's 2048 and the next one is 1024?
Like
Or
this,
like
this 2-way and 4-way.
Yeah.
So this was
that-
asked by the question. So you were asked just to find a total number of tag bits for caches that'll direct map, 2-way, 4-way, set associative, and full.
I mean, how do I get the number of sets? So for the first one, for the direct map,
It's on the name, right? It's 2-way set. So this 2 is that n.
Mm-hmm.
4-way set. I mean, it's just read it like this. Each set has 4 different ways. Each set has 2 different ways. That's why we call it 2-way set associative, 4-way set associative. Each set has 4-way, 4 different. Just think about it as 4 comparators. You need to search on that set.
I see.
Okay.
Yeah.
Other questions?
Yeah. Could you go back to the graph that have different set associate?
This one?
Yes. For example, for 2 ways, if the set number is 2, there's 2 tag. How do we distinguish which one is which?
Exactly. So this is like 2-way set associative, right? So you have 2-way for each of those sets. That's why we call it 2-way set associative.
Mm-hmm. Like the set number is 2, that there's the 2 tag. So we have to compare this.
No, we have 2 tag data set, right? Two tag data pair set. It's
Okay.
you have 4 sets now, right?
Mm-hmm.
But each of those sets, you have 2 different ways. That's why we need to have 2 comparators, right? Each of these sets, set 0, you have 2 options. Set 1,
Okay.
you have 2 options. Set 2, you have 2 options. That's why you have 2 arrows here, because you have to search for these 2. And that's the reason we are we need to adopt a replacement policy, least
Oh.
recently used or randomly, right?
Oh, so this one, this set associative is the two ways for this graph.
Yes, and that's exactly coming from that n-way set associative. That n determines how many ways your set can have, right? So this is two. Each of my sets has two-way, right?
Okay. Okay, yeah.
Other question? All good?
I just have a question. So on a final, for example, if you get similar questions, can the numbers be different?
Would you like the same number?
I would love to be honest.
Yep.
That would be very boring, actually.
Yeah, but it's gonna be the same way as we're solving this one, right?
I don't know. Nobody knows.
Nobody knows. I see.
Yeah. Right. So you're just dividing the total cache space by number of, that's right. Yeah, exactly. Okay, so that was for one level of cache, assuming that we had one cache, let's call it L1 or cache, and then we had memory, right? What if we have multi-level of cache? Because at the end of the day, we are talking about the memory hierarchy. So architectures, the recent architectures as of Pentium 4, 2003 or 4, they were starting to adopting multiple levels of cache. And from the closest level to the memory, to your processor, which was the L1, it had the lowest space, the fastest one, and then you had L2, which was a little bit larger, a little bit slower than L1, yet faster than L3, and then L3, and then perhaps your memory and your other type of memory could be hard drive and elsewhere, right? So let's see if you have multiple caches, multiple level of caches, how are we gonna adapt these methods towards those, all right? Let's have a question. All right, so assuming that we have a CPU with a base CPI of 1, everything is perfect, and the clock rate of the CPU is 4 gigahertz, all right? So the miss rate per instruction is 2%. That means 98% of the time we hit the cache, okay? So main memory access time is 100 nanoseconds. All right. So when we are trying to compute the miss penalty, having only one level of cache, which is this cache, without L2, the miss penalty would be what? 100 nanosecond, which is the access time of the memory for those cases that we need to access memory, and thus, what was those cases? What were those cases? Those cases were the miss cases, right? And we need to divide it by 0.25 nanoseconds per clock cycle. So the miss penalty would come as 400 cycles. So for those cases that we miss, for those 2% cases, right? We have to pay a price of 400 cycles because the access time in memory is pretty larger. So the effective CPI will definitely not be 1. You start from the base CPI of 1, but now you have, you need to pay a price, put some stall, right? Which is this, multiply your 2% of the time, multiply the 400 cycle penalty that you're giving up for this 2%, and that will effectively reduce your CPI from 1 up to 9 now, right? It's a different ballgame now. So from 1, because of only just that 2% and the very, very slower actually access time of memory, now instead of CPI 1, you're paying a price of having a CPI of 9, all right, on average. So that's the case when you have only one level of CPU. Let's see if we adapted a new architecture having 2 levels of cache. So instead of only cache memory, we had L1 cache, L2 cache, and memory. Let's see what would have happened, okay? So in this example, now we have L2 cache. So for those cases that L1 misses, now we won't go directly to memory anymore. First, we stop by L2. Let's see if L2 had this, right? And if it had it, so it's still good. We can just have L2 hit, L1 miss, and then we come back to L1. If on the case that L2 misses as well, now this is the time for us to go back to memory, all right? So now we have to define another metric, and we have to distinguish between global and local miss rates, because global miss rates would be the overall miss rate for the memory hierarchy. And each of those segments, if each of those architectures like L1, L2 has their own miss rate, right? Primary or local miss. So now L2 cache, now instead of 100 for memory, is pretty much faster, which is 5 nanoseconds. Okay, still slower than L1, but faster than memory. And the global miss rate to main memory is 0.5%. Does anyone know what this number mean? The global miss rate to memory.
Overall, the average miss rate.
Yes. So this is the average miss rate. So this resembles that your L1 had already missed, and your L2 already missed as well. Okay. So remember, 2% of the time, your L1 missed. Okay. Now by adding L2, overall, you have 0.5% misses. Okay. That means that the rest of the time, L2 could catch or could hit those misses of L1, all right? Now, if you want to compute the primary miss rate for L2 itself, because this was the global miss rate, right? On the case that both L1 and L2 missed, you can just easily compute it as for the access time of L2, this is 5 nanoseconds, right? And you divide it by 0.25 nanosecond, which is 20 cycle, right? So now you see if your L2, if your L1 misses and you go to L2, now instead of paying 100 cycle price, 400 cycle plus, right? Now you need to only pay 20 cycle. It's much better than having only one level of cache in this case, right? And we can easily compute the primary miss rate with L2 misses, okay? So those cases that both of them are missing, it's gonna be 100 divided by 0.5%, which is technically 0.005, and that's gonna be 500 cycle, right? So effectively, now your total CPI, you have started again from 1, you added those cases that L1 misses, L2 hits, right? And on the case that L1 misses and L2 misses as well. So this is both of them, L1
we
and
flip them, right? We
L2.
flip them.
This is L1 only.
We flip them, right? Because for the
What is it?
I said we flip them because for L1 it produces 400 cycles. Shouldn't we multiply 400 by 0.02 and we multiply 20 by 0.05?
For L1 was 400 here?
Yeah.
But this was the case, we didn't have L2, right?
Yeah, so when we have L2, we flip them.
So now we have, when we have L2, right, we need to pay the price for having L2 only. Instead of 400, it's going to be 20.
Yeah,
right?
but we multiply it by 2%.
Yeah, so this is your L1, this is your L2, and this is your memory, okay? So on the case that you didn't have L2, whenever you miss, you had to go to memory. So on each of those misses, you had to pay 400 cycle price. Now, if you have multiple level of cache, when L1 misses, on those 2% cases, you're gonna go to L2, okay? And overall, 0.5% of the time, L2 misses as well. So you have to go to memory. So those 400 cycle miss penalty for the memory should be accounted only for these times, only for this time.
So basically, if we did not have L2, then reaching from L1 directly to the memory is going to be 400 cycles.
Yeah, it's because access time in memory is 400, right?
Okay.
Right. But we want to make sure we access it as least as possible, as few as possible, because we have now a faster cache in between. So why not first stop by here? Because the access time here is 5 nanoseconds. Okay. So the miss penalty for those cases would be only 20 cycle instead of 400.
Yeah,
right?
but when we find the new CPI, we need to include all possible cases.
Yeah, I mean, if you have like L3 as well, you would have to consider the cases that L1 misses, right? And then L2 misses. When L2 misses is like L1 already missed, right? We are in L2. On some of the cases, L2 misses as well. And on some of the cases, L3 misses as well. So that's going to be your memory. So that's why we call it a multi-level memory hierarchy. So depending on the level of cache, you just go down and down and down. And every time you miss, and the next the next one also misses as well. So you have to pay a penalty, right?
Yeah, I just have a question. If you, for example, had L3, for the total CPI, it's going to be the percentage of miss times the cycles of the one below it, of the level below it, right?
Yes, which was L2.
Which was L2, and then plus the miss penalty for L2 times the cycle of L3.
Right.
It's going to be the percentage of percentage of L3 multiplied by the cycle of L1, which is 400.
Cycle of memory.
Memory, yeah, which we get it from L1.
Exactly. Yeah. That's right. So that was just you would have gone down. Yeah. So just pay attention to this keyword, global miss rate. It's the global miss rate for both of them globally. Each of them has their own primary or local miss rate as well, right? L1 has miss rate of 2, okay? 2%. But globally, this system has 0.5% miss rate, right? Because you have included L2 as well, right?
So if the globally was 0.5%, it means the locally for L2 was really small, right?
Yes, that's right. You can just make a division and find it. So now you see that the performance ratio is much higher now because you started from base CPI of 1 and you lost many of those because of this, right? Oh, I'm seeing another question here. How did we come up with this 0.5 nanosecond? Does anyone know? Does anyone know what this number, how this number came?
Is the frequency, the clock frequency?
Yeah. Okay, great. All right. So now we saw that when we have only one level of cache and we miss 2% of the time, so 2% of the time, we need to pay the price of having this huge access time in memory. Is the inverted value, right? Is 4 gigabytes is the inverted value. Yeah, that's the clock rate, or rate versus time would be inverted. All right. So we saw that for the 2% of the time that we miss we need to pay the price of accessing memory, which is pretty slower, right? It's 100 nanoseconds. So instead of CPI 1, now we have a CPI of 9, which is pretty slow, right? So we thought, okay, let's add another cache in the middle of these two, because we are missing 2%. Let's lower it even lower, because some of those misses might get hit by L2. So L2, instead of 100 nanoseconds, it has only 5 nanoseconds, so around 20 times faster than memory, okay? So you can compute it, the amount of cycle you're paying, right? It's gonna be 20 cycles. So remember, it was 400 cycles for memory. So this is like 20 times faster, this is the same. Faster 20x. So that was for memory. And instead of 9, the CPI will come down to 2.6, all right? Because in some of the cases that L1 misses, L2 hits, okay? So that's another type of questions you might get. Still, you see that it's pretty easy. All right, let's see if we have one more. Yeah. So we'll have one more question, and then we'll pause, and then we come back and we wrap up the course, all right? So the alternative method to computing the stalls, right? That would be by just combining the L1 miss rates, right? And the global miss rates, right? So 2% of the time L1 misses. So that means that the rest of the time, either L2 hits or L2 misses. And we know that 0.5% of the time, the whole system globally misses. So that would lead us with what? The difference between these two, multiply the access time for L2, right? And this will give us the hit rate for L2, the miss rate for L2, right? I'm sorry, this is the opposite side of the example. That's going to give us the stall cycle of those references that hit in the secondary cache. So that's the stall by the hit of L2, okay? So that's the difference between L1 misses and L2, all right? So if we were to come up with this number, 3.4 again, right? We could have computed from this side. Now, those references that we computed that go to main memory, right? We must include the cost of going to main memory for those misses, right? For 0.5% of the times we are going to memory, we have to compute their cost, right? So 0% of the time, we first check L2, we pay this price, we didn't find it, but still we had to check it, right? We check L2, so we pay the price of 20 nanoseconds. And then said, oh, we didn't find it, now we miss. We need to go back down to memory. So now I have to pay again 0.5% of the access time of memory, right? It will give me 2.1 as a CPI. Now adding 2.1 to that 1 plus 0.3 of those heat time is going to be given again 3.4. So we moved up from the heat access time again, right? This is like two cases of the scenario, which way you want to go. It depends on what variables are available, or sometimes you have both options, right? You might want to go from this side, the CPI of the base, and the time it takes when L1 misses, L2 hits, and the time that L1 misses and L2 misses as well. So you add these three cases, and you come up with 3.4. Does that make sense?
I have a question. So can you just explain what's the 0.3 and how did we get it?
It's actually the access time. This the CPI of the access time of L2. So when you have access time in L2, what does that mean? L1 had already missed. Otherwise, there's no need to go to L2, right?
Yeah.
So that's one case. So your L1 missed, L2 hit. So that's 0.3. On the other case, that L1 missed, L2 missed as well, so you need to go to memory. So you have to pay the price of 20 nanosecond cycle for L2 and 400 cycle for your memory.
Yeah.
And those cases are how many times in ratio is 0.5%. So you multiply and you're going to come up with 2.1. And then you add it up to the 0.3 and the base 1. That would be again 3.4, right? So this is another alternative answer for the same question here we had. Yeah. So this way we went with the stalls, and the other side we went with the access time actually.
I have a question.
Second way seems easier. Yeah, it depends. Yeah, both of them are intuitive. Yeah, sure. There was a question?
Yeah, I have a question. So if we had L1, L2, L3, and then when we were solving for L1 and we find the cycles, would the answer be for the whole thing, for the whole hierarchy thing, like to reach the memory? So for example, when we were trying to solve for L1, we got 400 cycles.
Okay.
We had L1, L2, L3, and we solved for L1 and we got a number of cycles. Would that be until it reaches the memory? Or in that case, it would change. It would be only to L2.
No, it would be until the time it hits, and we prefer to hit as highest as possible. So if L1 missed, we prefer to hit it at L2, right? We don't want to go to memory when L1 misses.
Then L2 would go to memory.
Sorry?
And then L2 would go to memory if it misses?
No, L2 would go to L3 again.
L3 would go to memory.
L3 would go to memory, right.
Yeah, in this
So
case,
that's why you have a hierarchy. You prefer to just fetch it from one level lower, unless that one level lower was the memory.
But why did we, in this case, fetch from the memory from L1 directly?
Where?
In this question, in L1, we got 400 cycles.
No, so in the first part, we didn't have L2.
Oh, okay.
Yeah, so that was the case, no L2.
Okay, I see.
Yeah. So that was an example with primary cache, just one, like L. Okay. Now here we added L2 cache, and we compared 9 went down to 3.4.
Mm-hmm.
And we computed both ways how we're going to compute 3.4 here. All right. So adding L3 would have perfectly made sense to bring this down a little bit more. All right.
Okay.
Yeah. So there are so many things left in chapter 5, and you have a matrix multiplication code, which is called GEM, or general matrix multiplication, which is actually by its name, you're multiplying two matrices. And then we, in this chapter, it gradually starts to optimize the code to use cache locality of memory. And so since we don't have much time on this, I would strongly recommend you have a look at it for your own information, especially that many of the machine learning applications are using a matrix multiply, or GEM, right? So in your future work, perhaps you might see this quite often, because most of the machine learning and deep learning models are actually multiplying matrices. So the way you optimize a matrix multiply by caching different blocks, different elements, how we're going to traverse those matrices, columns and rows. These are interesting problems in computer science, and you see by an unoptimized one up to optimized one, you're gonna have a huge improvement. There were dependability issues and also other encoding issues. So these are all outside the scope of the course, because we don't have much of time. So we will stop at the end of this example, which was slide 60. Okay. Yes, it is. So let's have a 10-minute break, and we're gonna start at 7:35 to sort of wrap up the course with some examples on chapter 4, pipelining, and also some quick review on cache. Okay, so see you guys back in 10 minutes.
Guys, can you hear me?
Yo,
Yeah, we can.
Okay, I'm gonna share a video, I guess.
Yeah.
Yo, did you guys look at the Moodle and the final exam?
I still can't find it.
Did he?
Wait, did he link the exam?
I can't find it. Apparently, it's under the lectures. I can't find it.
If you go on Moodle, I can't share my screen as I should. If you go on Moodle and you know the slides that he uploaded today?
Yeah.
So like that's week 13, but if you go under that, it says final exam. Let me send you the link.
Final review?
It says final exam, and under that there is there's a sample. Okay, check this link.
I see like lecture 10 and lecture 11. But what's this? Is this a different class?
Let me check.
This is a different course. This is 2018, 2019.
This is from last year.
I'm about to. Okay, no worries. Then he didn't put it.
Yeah, because it says you need to enroll and it says you can't self-enroll.
Yo, guys, it's there. Trust me. I just opened it.
What?
It's there.
No, it's because it's from last year. That's why.
Yeah,
It's
but I can't
2018,
even,
2019.
But if
I
you
can't
open,
even get into it though.
that's weird. Wait, let me
Can
see.
you download
No, you
it?
can't. You can't get into it because you never took this course before.
Yeah, like that's
Someone just posted in Google Docs and just share the
Google
link.
Docs.
Yeah, can somebody do that?
Yo, guys, it's on there. So basically, if you open 2021, and then you put course slides, and then you go all the way down, it says lecture 11 final review.
No, that's the review,
Oh,
not the
okay.
exam itself.
Are you guys talking about the exam?
Yeah.
Oh, I think this is like a bad place for you to discuss. Right?
That happened to me in grade 12 once. My teacher literally leaked us the whole exam.
Yeah, I'm gonna send you guys something. This is so jokes. One of my friends, his prof was sharing tabs, and he had one of these browsers history or some shit saved. It's so jokes.
Oh no.
Okay. How's it going, everyone?
Pretty good.
What are these links passing here?
That's shady. Oh no.
Oh, that's a Facebook link. That's why.
Send
Bro,
a peek or
Facebook links.
flicks.
Sir, we were asking if you're gonna post the final, like a sample for exam that we can practice on.
So actually, I posted sample questions for chapter 4 and 5, and we are reviewing the exam right now. So what else you want me to do?
Yeah, okay, let's do that first.
Yeah. So I mean, questions are pretty standard. If you have attended the course, you've already had accumulated many of the points already, and we redistributed to final. So there's I'm sure all of you are gonna get good marks. So let's wrap up quick here. So in chapter 4, we talked about data path. We started to use Verilog, and this is the main data path of the RISC-V that we had. So we started here with the program counter, which receives the address. Okay, so this address either going to be fetched and incremented by a number 4, PC plus 4, to continue going fetching the next line, or you're going to head into a branch, and the new address will be posted back here. So you're going to have either of those, and we gradually complete this data path with having multiplexers and control unit and so on and so forth, right? And then we started to decode the instructions in this side. Then these were the register files, including your read and write registers. We talked about the controls for the registers. For instance, when you want to write, there should be another control wire here to this, determines when to write and when to read. We had all of the instructions. Many of the instructions had either 1 or 2 read, right? That's why depending on the control signal that comes here, you need to have read data 1 or read data 2, or both of them available for us. Then we went to the actual execution, right, in pipeline, which you manipulate something, you add something, you compare something, you shift it, and you do other things, or perhaps you just do a branch, right? Then finally, you're accessing memory in the mem stage. In the load stage, we had to access it at the load stage. In the other operations, the other operands, we actually do the actual job after execution, and then we do save it, right? Recall, and that's how we could able to forward the results to the next cycle of the pipeline, right? At the same time when we are saving it. And then finally, it was a write back, and the whole cycle started. So that was an overview of the data path. I'm not asking you to memorize this scheme, although you have done your labs and pretty much you understand this shape. You know what are these segments are. I don't want you to memorize them, but you need to know what are their functionalities. Okay, you don't have to memorize again your control signals, like what was 0004. I'm not going to ask you to just complete AND or add, but you need to understand that we have certain signals at center control signals at each of these locations to determine if the output of the mux would be using certain behavior. If we are going for the branch, what's going to happen here, if we are branching or not. So these control signals will determine how we're going to execute in a data path. Okay, so this could be a sample example in your final sample question. You're given an address, right? So you have to decode it yourself. All right, you're given your green sheet, so you understand which is which, actually, which type is it? Is it R type? Is it for branches, right? Is it for load and store? So you understand which segment of this are referring to what. For instance, in this case, the 7 least significant bits are for opcode, and then you have the first 5 bit of the immediate here, and then you have a func tree, which you can find it in the green sheet. Then you have your source 1 and source 2. That means that we are using both of these, and then you have another immediate. Okay, so decoding could be a pretty easy question you might get.
So
it just shows you how you're going to use your green sheet. Okay, that's all.
Would you give us the numbers the numbers at the bottom for the bits so that we would know which?
No, you can find them easily from green sheet. It's there.
You will tell us what type it is, right?
You can find all of them.
No, but I mean, how would the question come? Is it going to be an empty page and then we choose any type and then we fill it based on?
No, I'm going to give you an address. You can decode it. Yeah.
Oh, okay.
This could be one way. Yeah. And then I might ask you what type of address is this, and then what are the sources and destinations, and so on and so forth. So that would be pretty easy for you. It might be a conversion of binary to this decimal or vice versa, which is pretty normal and easy for you now. Also, again, you're not required to memorize this, but you just have to understand that, okay, for each of the opcode we had certain ALU control, because for each of those different type of opcode, different segment of the data path would be activated, right? For instance, for these operations, right, addition, deduction, and or other things, some of these were activated, some with X were don't care, which doesn't matter on that specific scenario. These were the broad category of the types you already saw, right? Right, all type, I type, S type. So these are exactly, and the fields are in your green sheet, so you can use your green sheet to decode the instructions if necessary, right? And then mapping those controls on top of your data path, you would add something like this. So the same old data path with control signals mapped on, right? So questions?
Sir, the questions you posted on the exercises you posted on Moodle, do they reflect the type of questions we can expect on the final? Like, are they going to be similar or somewhat same ideas?
So yeah, some of those might be similar, and also the slides that I'm just reviewing right now, I'm giving you many hints about the potential questions, right? But the format of the questions, the format of the booklet you might get is going to be the same as your midterm. So the way the outline was, so it's sort of similar to your midterm. Yeah.
Thank you.
Yeah. So we mapped the data path with control, and each of those signals, the control signals, would determine some part of your data path, right, to get activated, depending on the type of the signal. You see now, the R type was activating this ALU control, because now you have to access memory now, right? And also this one, ALU opt. For the case of load, this segment of your data path would be activated, shown in bold blue, right? For the branch, of course, the branch unit would be activated, and the outcome of the branch would be passed to your next PC, and so on and so forth, right? So that would be like pretty straightforward. For the rest of that chapter, which we talked about pipelining, again, you might see some questions about the performance of a pipeline, just like what I did in two lectures ago. The questions would be pretty similar to what you saw. I'll review it again now. So as a recap, we talked about 5 stages of RISC-V pipeline, because we thought the resources are limited. So now assume this is a 4-stage pipeline. The resources are limited. Instead of just doing them sequentially, instead of the second cycle that needs to access this machine to wait up to here, right? Why not, by the time the first task finished with the first machine, the second task can use the first machine, right? Although we don't have 4 pieces of them per task, but since the tasks should be done one by one, when the first task finishes doing its first pipeline and it's on the second pipeline, why not use the first pipeline for the second task, right? And this will translate this problem in a sequential way to a pipeline way, right? So in RISC-V, we talk about 5 stages of pipeline: instruction fetch, where the instructions are fetched from memory. Then in the decode, just like a manual decode, you saw, you have to decode the instructions, see what the type of type the instruction is, what are the registers, and you need to read the registers, right? And that's why we had hazard in ID in most of the cases, because we need to read the registers. So instruction decode, although the name resembles decode, but you have to make sure that there is an AND register read as well. You need to know the registers. If the data is not available, there's a hazard. In the execution stage, we were talking about the actual execution, right? The actual operation. If it was a branch, the actual finding the address of the outcome branch, or if it was a store, load and a store. So that was the actual execution, right? On the fourth stage, we had the memory, where we had to access memory operand, and finally we had to write it back. Okay, because of those pipelining scheme, we can have 3 different hazards. We talked about them extensively two lectures ago, or 3 lectures ago. You can refer to the videos if you missed those lectures. So we have a structural hazard, where we have the data, but we don't have the resources to use them, right? We have data available for our RS1 and RS2, but the execution is busy with other operations, so we need to wait, right? That would be a structural hazard. We didn't see much of that in this course. It's normally for an advanced computer architecture, but it's there. I just wanted to showcase it to you. And the other 2, we saw it in this course: data hazard and control hazard. For the data hazard, we needed to wait for the previous instructions to make us ready, right? And provide us with the data, with the updated data, because it might be the case that there are some other operations on top of one data, and then you want to access $3, and $3 hasn't been updated yet, so you have to wait for that, right? And a control hazard, which most likely happened when you want to branch, is you don't know what the outcome of the branch is, so you don't know if you want to, for instance, exit the loop, or you want to remain in the loop and do another iteration of the loop. So that's another type of hazard. We call it control hazard. So the questions normally come from recognizing, identifying what type of hazards does it have, and then, for instance, put an arrow to the hazard, or the specific hazard, and relate it to the specific variable the hazard was related to. Okay, so these were for the base pipelining without any optimizations. So gradually we built a more optimized pipeline using forwarding, which you can see with this blue arrow here, for which, when the result of the outcome of the execution pipeline is ready, right, at the same time that we are sending it on the bus to memory, right, then to write it back in memory, we can forward it so that the next stage of the pipeline, next instruction, which is sub here, can utilize the intermediate result we computed in their ID stage. Recall, in ID stage, we had to read the operations, right? So we can do it at the same time. So in pipeline method, that would be floating this way, right? But in the actual data flow, it's as if the execution, right, is forwarding the results back to the ID, because add was here and sub is here, okay, in the ID stage, right? I'm forwarding back the results so that the sub that's coming one behind this have access to the outcome of the execution, okay? So, but when we show it in this scheme in a pipeline, it's as if I'm sending this towards the next, right? But in real world, think about this as this sub is here and add was here, okay? So you forward it back. So now it can, because this one was adding x2 and x3 up to x1, so the result of x1 was unknown, where we are here, and we needed to forward the result so that at ID of the sub, when it's subbing x1 and x5 and the result to x4, we need to know the actual value of x1, right? So that's called forwarding. The only case in forwarding that we can't do forwarding from the X was the load instructions, for which in load we need to wait up to the memory because we are loading from memory, right? So at the end of the execution, there's nothing determined so far. We're just going to memory to find the value and then load it from memory. So So that was the only case. For the other cases, for the data hazard, we can forward it from the execution. All right. So even with forwarding, in the case of a load, we needed to have stalls, at least one stall, because with one stall or one bubble or one no operation, you're able to send this to the ID of the next iteration. Otherwise, there was an hazard. Okay. One of the other optimizations we could have done. Oh, there is something going on in the chat. Okay, nothing important. All right. So there was another type of optimizations we could have done was, we talked about scheduling, right? We manually or some compilers or some architectures are able to do an automatic rescheduling, which is a pretty hard task. In this case, that was a very small example. That was just two additions, right? A is equal to B plus E, and C is equal to B plus F, right? On the no scheduled, rescheduled case, so we are loading this or that, and so I actually this is E, right? And for B, we are loading the 8th address of x0 to x2, and then right away we're going to add this to generate the result for A. So because we are accessing again x2 in the next iteration, so that would be the data hazard, right? The same thing will happen when we load F and B, and then we want to add the value of F and B to generate C, which is for the case of x4. So we thought, okay, can we reschedule the code in a way that the structural or the so in compiler they're going to call it is functionally correct. So the output is still functionally correct, and also the result would be the correct result. So you both is functionally correct because we are having additions and loading and additions, so it's functionally correct still, and the outcome would be correct as well. So we are trying to put as much space between two axes of x2 here, and also two axes of x4, right? Let's see how we're gonna put these two further away as much as possible. So we thought, okay, if we load this first, and then right after that, instead of loading B, let's load F now, because it's not going to make any differences, right? However, or I'm sorry, I mean, we could have done that, but the way it has been done here is like E and B, but instead of the addition of B and E, we loaded F here, okay? And then after this, we give enough of a space between these x2s so that with the forwarding, we are able now to surpass the data hazard. So we don't need to put the stall anymore, right? It was load, remember it was load, even with forwarding, we needed to put the stall. Now with one instruction in the middle and with forwarding, we are able to push past the stall. So we are saving stall here. The same thing happened for x4, right? That's why we loaded all three together instead of to load and add, store, load and add, and store, right? We push all the loads next to each other, and then we added, and then we stored the result of the A, and then we added the next one, and we stored the result of the next one, okay? So in this case, we saved 2 cycles from 13 to 11. So that was a manual scheduling. If you're given some similar questions in the exam, that would be as easy as this. I'm not gonna just ask you to reschedule a matrix multiplication. It would be just as easy as an addition or a deduction, okay?
I have a question.
Yeah.
So the main point that we should grab from here is after we do the manual scheduling, we need to have a stall between reusing the same variable, right? Which is B in this case.
I mean, sometimes even with manual rescheduling, you're not going to be able to, you know, resolve all the stalls.
Yeah.
Yeah.
So, yeah, okay.
Okay. And then, so that was the portion related to data hazard, right? Now for the branches, normally the branches, the outcome of the branch, right, must determine before fetching the next instruction, right? So in the case that we wanted to fetch the instruction at instruction fetch, some branch optimizations allow us to anticipate the branch at ID, right? So we save one bubble or one stall there. And we can do the forwarding after the execution for that. So we're gonna save, instead of 3 stalls, we might save it to even 1 stall, okay? So we had, let's review an example that I reviewed in the course. So you're gonna be given a code, a simple C-like code or a Java-like code, which is the same. It's gonna be like a loop or something. In this case, like 2 increments with 2 arrays, right? And the final would be all added up to another array. Then you're gonna have an increment of your induction variable, and then you're gonna have your loop bound check, and then it's gonna be going on in a loop, right? So I might ask you just to write down the equivalent code for RISC-V, which is pretty easy for you guys now, for such an easy case. And then I might ask you, I'll give you a table such as follows, and I'll ask you identify the hazards, okay? The hazards for, and then write down a hazard, normally with 2 different colors, one for the control hazards, write it as control, and data hazards, and write down the specific hazard for that specific variable, okay? So in this case, you understood that, okay, we are loading and then we are adding right after that. So this $2 is getting loaded, and right after that we are adding it, okay? So there's no optimization so far, so we have to wait from the write back to pass it to the ID, right? We have no forwarding. So there is this WB write back to the ID of the next instruction, which was the add I, because it was using the $2 that was loaded, okay? And this is D, actually. LW is D. Seeing something on chat. Yeah. So then again, the same thing happened for $3. You load it and then you add it up. So this WB to ID, okay? So you have to write read after write $2 or $3. So this raw, I mentioned that this is a data hazard. It's referring to read after write, right? And $2 or whatever the variable was. So we are reading this after it's getting read, and this is not good because the value would change. So we have to wait 3 stalls, 3 bubbles. Why? Because this ID should pass right back. So 1, 2, and 3, and then from here at C6 we are able to access the result of the write back if we have no optimization, right? So, and just like that, you need to identify the other problems. So for instance, this ID and W are on the same cycle, which is a read after write, because this is the addition of the 2 addition, right? So you loaded this one, you loaded the other one, and then you want to add them. And so that was another one. So read after write $3 and $2 at the same time. Then you wanted to store it. Again, you had another read after write for $5. Then the one after that was fine up until the point you reach add I $4 to the branch. So the branch, when it is trying to understand the bound check, right? If it doesn't know the value of I which was added, it has to have a stall. And remember, this is not a control hazard. This is a read after write hazard for $4, which was this increment. I mean, this case is pretty easy. Now the modern compilers can easily understand if it was an induction variable incremented 1, so that would be easily solved. But assume that it was a more sophisticated one with like I plus 2a divided by 2n, right? So this increment of the loop was not easy to compute right at compile time, so you had to have this stall as well. So up to now, all of them were data hazards. So what remains is the actual outcome of the loop, right? Are we going to go back to do, or are we done with the loop and we're going to exit and we sequentially execute the rest of the instructions, right? And that's going to be a control hazard, and it would be determined from mem to the instruction fetch. No optimizations in the loop, no optimization in the branch. So you have to wait at the end of the mem, because in your data path, you remember the outcome of the branch was determined after your execution and right before your memory. So you have to wait from memory. And the outcome of the branch, when it's not known, you don't know what instruction to fetch, right? The next instruction to fetch could be L1, right? Or could be these instructions that were here. So you don't know what to fetch. That's why there's a control hazard. That's for an unoptimized pipeline, right? So for all of them, you have to spend 3 stall. So that's the zoom in version. Questions?
Yeah, in the exam, we just need to fill this chart and write the code.
Yeah, you're going to be given such a table, and you're going to write, for instance, your RISC-V here, and then you have to just determine what are the hazards, okay?
Do we need to like draw the arrow
Yeah,
line?
yeah. So these arrows are important because it shows your understanding of at what level, at what stage of the pipeline the hazards occurred, okay? You need to understand if it was from write back to ID or it was from mem to ID, right? That's important.
For example, if you give us a high-level language, do we need to write down the RVS language, like just in the example?
Can you repeat your question?
Do we need to write any code for this example?
I mean, you might, in the first part of the question, you might have asked to write down that small C loop, that loop to a RISC-V, right?
Okay.
That might be one part of the question,
Okay.
which is pretty easy for you. Or you might just be given such code right away. And then you have to identify the data hazards and write down what hazard it was related to. It was for like $2, 3, and then you have to put an arrow that, okay, if you run this pipeline, you might have to wait like up to the W back of the right back of the $2, $2, because you want to decode it later, okay? In essence, what that translates, it would be this with the stalls, but giving you such table and asking you to put the stalls would be pretty much messy, because you might just miss a stall or 2, and then here you realize, oh, I missed 1 stall. Now you have to just remove all of them and assume you were using pen, and that's going to be a nightmare. So, but in essence, that would be the outcome, right? These are from the instruction, the control hazard of the previous side, which we didn't know, are we going to come here or we pass and execute the rest. That's why we need to have 3 stall here. But the rest, these 3 stalls was for the accessing of the read after write issue for $2, because now I have to halt this instruction at I, 3 more bubble, so that the ID of this instruction will occur after write back of the previous one, okay? Just like this for W3, just like this for W5, and then the store of W5, and this is the increment of that I, okay? In essence, that would be translated to this. So the final instruction count would be 30, right? Although you had 1, 2, 3, 4, 5, 6, 7, although you had 8 instruction counts, and in a perfect world of pipelining of 5, that would be what? Equal to 12, right? Because how many instructions you have, whatever instructions you have, you just have to add 4, because you have to pay the price of closing the pipeline, the last 4. And so you can easily compute this 12 from this. A pipeline of 5, 1 would be for the CPI of 1 would be for everything, right? But then you add 4 more because your pipeline is 5. So in a perfect world, without any stalls, with 8 instruction counts, you would have 12 cycles. However, adding this many stalls, it expanded your 12 cycle to 30 cycles. And that's pretty easy to compute because you had 3 stalls for the $2, 3 stalls for $3, 3 for the add of $2 and $3, and the other 3 for the store of that, and then the increment, right? Before just to do the branch. And that was the branch itself. So 6 multiplied 3. So you had 18 stalls added to your 12, no stall, and that would be 30, right? So that's why you see all this 30 here. So you had 6 of these 3 instances. So easily you can compute some performance evaluation. 8 instruction count, you just count the line. Number of stalls per iteration was 18. 6 times you had 3 stalls. And then you can easily compute the CPI per instruction. So your new number of cycles, clock cycles, would be your instruction counts, which was 8. Your number of stalls, which was 18, and plus 4, which is coming from a pipeline of 5. You add them up, and that would be 30 divided by the instruction count. So your CPI would be 3.75, right? Clock per instructions. Then you can easily compute the throughput in MIPS, which is 10 to the raise of 6 mega, right, per iteration. This will be given to you either by nanosecond or or hertz, right? So it was given to you 500 multiplied 10 to the raise of 6, and then you just use the CPI you found, and then you scale it up to MIPS because we are expressing in MIPS, and then that would be your final throughput. The throughput is actually the amount of resources you utilize from your processor, right? So out of 500, you're able to execute 133 out of that because your CPI is 3.75, is not 1, because you had the stalls, right? And that would be the explanation for that throughput. Difficulties? Yeah, it would be the same. Yeah, not much more difficult. I mean, these are pretty easy examples. These are just quantitative examples. I'm sure you're good at, because you've already done so many coding and implementation already. I don't want to just write down code in the final exam. That would be minimal if you're asked for that.
Russell, I have a question.
Yeah.
Where did we get the 500 from?
It was in the question statement here. The processor clock cycle is 2 nanoseconds.
Okay. And
Yeah.
how does it become 500?
Yeah.
How does it become 500?
It's an inverted value of 2 nanoseconds, right?
Okay. So it's yeah, I see. Okay.
Oh, I'm sorry. This is -9. Yeah. So it goes up. It's going to be 10 to the raise of 9, and then this is 1/2, which is 0.5, and then you adjust the mantissa and the exponent. So,
Professor,
what is it?
do we need to for the store question? Do we need to, like, in the chart? Do we need to write down where the store is?
This chart, you mean?
In this chart.
No, normally you're not going to give this chart because it would be messy to write. You don't have to write it. You just have to find arrows and then put from to with the arrow-like shape, and then write down the hazards. And then you have to guess how many stalls it takes, which is pretty easy, which is 3, 3, 3, 3 in a pipeline of 5. So you just come up with this. So this won't be given to you because it's messy to write.
Oh, okay.
Yeah. I mean, you can write it for your own in your draft sheet if you understand it better.
Why do we need a first 3 story here?
Say that again.
Why do we need the first 3 store, like the first
So
line?
these first 3 stalls are actually the outcome of the branch, right? You don't know what to fetch in the next instruction.
Oh, maybe it come back, so we need.
Yeah, I mean, you could have just write it here.
Okay.
But yeah, this is the next iteration.
Professor, would the number of stalls always be 3?
On the unoptimized case, I mean, it has some relations with optimizations involved. And in this case, we are using a 5-stage pipeline, right? If it was 14-stage pipeline, that would be a different story.
Okay.
Yeah. Because you need to find a way to align this, right? Instruction fetch, ID execution, mem, write back. Now, if you want to fetch and the write back hasn't been done, so how many stalls, how many bubbles you need to have? 3. Because after that, this ID comes from here to here. All right. So normally these questions might have several parts, and then gradually you're going to be given more optimizations in the question statement. So some of the stalls might be resolved. Okay. For instance, in this case, the optimizations are as follows. In the register file, it's possible to read and write at the same time. So we might be able to resolve this write back ID. If nothing else changes here, we can read and write at the same time. So while this is writing, it can read the output of the write, right, in the ID stage. Forwarding path have been introduced. So now you know that the forwarding is on. So you just make sure that the load can be only forwarded from memory and the rest can be forwarded from execution, okay? And for the load, for the branches, we have another optimization for which program counter calculation for branches has been anticipated in the ID stage. So instead of putting 3 stalls or bubble to make it work at IF, now we can pass 1 and bring it towards ID, okay? And also we can use forwarding as well. So that would effectively reduce 3 to 1 for us. Now, parsing down using the forwarding, you're gonna given such table, right? Again, you don't have to put the stalls, but you have to just find the forwarding path, and then you're gonna be given another column to write the forwarding path. For instance, here for the case of $2, now we are forwarding from the mem stage to an X stage, right? That was the mem to X forwarding. Because of that, we only needed 1 stall here. If it was not load here, if it was add, for instance, we could have survived without any stalls, right? Because just we were doing X to X right away. The same thing happens for $3, the next one, because you loaded it and then you add I it. So the same thing, you need to have another forwarding path. So in this case, we couldn't avoid the stalls. So 1 stall here and 1 stall there. And you see when you have a stall, it's like a stall in 1 column, right? Because you're stalling the whole pipeline. So this is like nothing happens here. But because nothing could have actually happened, because the issue is one after another, so there's no need to write it down, right? Because the next instruction would be fetch here. The next instruction would be fetch here. So there's no need to write all the S's down. Okay, the interesting point happens here to save us a lot of stalls for which we don't have any loads here. So this add store can be all forwarded in the pipeline of the data path from XXX right away. So they are just passing through the pipeline anytime they need. The next instruction in the previous stage will use that. Again, the next instruction in the previous stage can use that in the next pipeline, right? So that's why all these three gonna get resolved. We reach up to the point that we have the branch, and because of the optimizations in the branch, we can anticipate it in the IDE stage, and then we use the forwarding path, because the outcome of the branch could have been potentially determined at the end of the X, right? The X stage, this is the branch, right? After the execution, you know the outcome of the branch to pass it later on. At the same time, you can write it in memory, but you can have a forwarding pass right away to send it to the previous stage, okay? Okay, so now, instead of those 6 multiplied 3 stalls or bubbles, now we have 4 instances of only 1 stall, right? We've saved so many stalls now. That was for the control hazard, for the branch. The rest were for data. That was branch. I don't know if it was branch equal or branch NE. Yeah, B and E was not equal. So you had 8 instructions. So 8 instruction count is 8. You had 4 stalls. These 4. And your CPI would be basically your instruction count 8 plus stalls plus that 4 of the pipeline of a 5 divided by IC. So now your 3.75 has been reduced dramatically to 2. So that's why your 5 out of those 500 megahertz of your CPU, now you're utilizing half of it, right? Because you have CPI of 2. If it was 1, that would be 500, which means you're utilizing all the potential of your CPU as your throughput, which is a perfect scenario, right? So now your CPI is 2, you're using half of it as your throughput, which is still good. You're utilizing your throughput, your final throughput of executing this code is not bad. You're actually, because of resolving all these hazards, you manage to utilize half of your potential CPU speed, all right? Now, we have introduced another optimization, which is static branch prediction. Recall in chapter 4, we had branch predictors, so dynamic or static. In this case, it is a static branch predictor, and the statement says static branch predictor for backward branches, which is statically backward always taken. So whenever we reach here, we know we don't care, we come back to L1, right? The outcome is always L1. That's why we kind of call it backward taken, right? So let's see if it does help us with the stalls or not, okay? For sure it does, because at this point now, the execution, which was the outcome of the branch, right? Could be determined right away to come back to L1, right? And the same as stalls are also there because of the data hazards, but at $4 and then $3 and $5, 2 and 3, right? So we saved one more stall here. We removed that control hazard because now we always know when we reach here, there is L1, backward taken, okay? So now instead of 4 stalls, now we have 3 stalls, and our CPI is even lower, which is better, 1.8.75. So now our throughput is even higher than 250, which is 266 now. Okay. So now we are in a much better shape now. Now, finally, by doing rescheduling, again, removing this, and also this right after the load, to give this $2 and $3 some space, right? For this case and also for this case. So put the loads together and then put the adds together. We can also, there was another optimization which was a branch delay slot. You don't have to know it, but there just to as an information, there is some hardware in modern computers that delays the branch. So you can do the branch, and after you can save the previous result of the $5, right? So in this case, if you reschedule your code this way, now you're going to see that the final outcome, you put the loads together and then you add item, so there is no near usage of $2 here up to this point, so it's good. $3, the next usage of $T would be here again, very good. You I++ right away, which didn't make any differences here, so you bought some time for $2 and $3 to get affected past their memory or execution stage with forwarding, so you can use them without any issue. So finally, you're gonna see that the rescheduled code, right? Load, add branch, and the delayed slot for the store will effectively resolve all the branches, right? Now you have 8 instruction counts, no stall. And because you are using a 4-stage pipeline, nevertheless, you had to pay a price of 4 more stalls because at the end of the day, you have 5 stage, right? So the perfect scenario for an 8 instruction counts is 1.5, right? Because you pay 8 plus 4 divided by 8, which is 1.5. And out of your 500, you're using 333, okay? So that's the perfect scenario for this example. So you might be given very similar question to this. Gradually, you build up the pipeline with other optimizations, right? This branch could be another method, like instead of backward taken is always forward taken, right? So that would behave another way. So that would be effectively for chapter 4. Any questions? All good?
So Professor, for the increasing that, like, could you go back to slide?
To slide. This one.
Yeah, here. For the third line, I mean second code, third line, the addition here, we don't need any store here.
No, because this is I++, right?
So for any I++ plus itself, we don't need any storage.
Because you knew what I was, right?
Okay.
Yeah, we can do the I++ right away.
Okay.
Because before starting here, you knew what I was. When you start here, you already check I with N, and then you start here. So instead of doing this, after you loaded them, because you need to load the right iterator, right element of that array, right? You don't want to load base I+1 or I++, which is incorrect. You load them first. After you loaded them, you can do the I++, because these increments were not important. They were like some constant, like 5 and 7, right? Okay.
Okay.
Other questions? Is anyone sleeping? Maybe. Okay, so so that would be effectively your chapter 4 review. So the type of question you might get are those that I shown. Okay. It's not that hard. I mean, we just reviewed it. It's not that hard. Chapter 5, you already saw many of the questions you're gonna see right? You just have to understand the hierarchy of memory. The closer to the CPU, the faster it is, the smaller the size is. So this is your cache, perhaps L1 or L2, or this is your one level cache, and this is your memory, right? So your hit ratio is a number of hits per accesses, and miss would be 1 minus hit. And we talked about different type of caches. Direct map, which each block of memory is going to be directly mapped to one block of cache, and then you just do a mod. Block address mod the number of blocks. Here it was 8. You could easily find that all the grays will be mapped in 001, all the blues are going to be mapped to 101. Here you might be given some memory addresses sequentially, and then you might be asked to just find if it was a hit or miss and what was the tag and data here, right? For instance, here the binary address 110 comes, so you know that you have these indexes. So this is referring to 1110, which is this. The validity bit are always none or not set when you start your computer or processor, and when it boots or when it was accessed, it's going to get set to Y, which is 1, right? It's a Boolean flag. Then this will determine the index. This will determine your tag, right? So at index 1110, the tag would be 10. In both cases, nothing was there, nothing was set. The valid bit was not set, so that would be a miss, right? And that's why you need to come back in from memory and then find the data corresponding to the memory address of 10110. So that would be equal to some data, right? But this access would give us a penalty, right? And so on and so forth. So you might just get given some more instructions. You have to just find the index and the tag and then see if it was valid or not, and then if it was missed or not. In those two cases, we were accessing the same block 1110, which already was set. The tag was the same, so that shows that the block is the same, the tag is the same, it's valid, so the data is there. It's already fetched in cache, so it's a hit. I don't have to go back to memory to bring it up. It's already there. It's the same data. I'm just going to use the output of mem of 110, which is whatever number. I'm going to use it. It's a hit. The same goes with this. The same block, the same tag, and then it's a hit. Okay, so that's just a binary to decimal translation. So this number is 26, and so on and so forth. Question?
Yeah. So what does the V stand for?
Valid bit.
Okay.
So assume all of them as non-valid. So this is valid bit. At the start, everything is non-valid or none or 0. When you access it once, you set the valid bit to +1 or valid or Y, right? And these were the other type of cache. So direct map, we saw that. So for 12, you just have to get a mod of 8, and that would be 4. It's going to be only found here. For the set associative, depending on the value n way set associative. This n would determine the number of sets we have to search for each of those blocks. So n is 2, right? You have 2 blocks to search for, and when you go up to the highest level of what you have, that will effectively be called a fully associative. Each of those could be placed anywhere, right? That's why we call it fully associative. And just today we talked about the position. So in order to find a position, you already know that you have to get a mod of block number with the number of block for the direct map, and for the set, you just have to do a mod of block number to the number of sets, and you're going to see all tags of all the elements must be searched inside. So, and that would open up the replacement policy, either random, rand, or least recently used, right? Because all the tags of the element of the set must be searched, right? And for the replacement, we have multiple choices in their set, depending on the result of this. If it was 2 or 4, right? You need to use either random or LRU. And for the fully associative, the blocks can go anywhere. Thus, all tags of all blocks must be searched, right? A general memory address would be this: blocks, offset, index, and tag. And normally, if you're asked to find each of those depending on the architecture, so you're going to given the overall 64, 32, 16, or whatever, and then you start using the information given to figure out each of those. And then depending on the number of blocks, you can just find the final size of the cache, right? As if we start from a one-way set associative like this, which is a direct map, to a two-way set associative. So we have 2 pairs of tag data, or 4-way set associative, 4 of these, or 8-way, since we have 8 blocks, so it's a fully associative, so could be going anywhere, right? Question. Life is hard, yeah. Good question. So, assuming cache, we just talked about it half an hour ago, and so what was a 4-word block size? So remember, in RISC-V, each word was how many bits?
4.
It's 4 bytes. How many bits? 32, right? Or 4 bytes. Because each byte is 8-bit, right? That's why we call it 8-bit byte. That means each byte is 8-bit, right? So each block is a 4-word block size, all right? So we call this one block. All right, for each of these words, which is gonna be 4 bytes, right? I need to have 1 bit allocated because I have 16, right? And I need to have 4 bits to understand which of those are gonna get to. And that's why I need to allocate 4 bits to address this. Does that make sense? We talked about it 1 hour ago. Yes, okay. Good. So out of 64, we used 4 of them because we need to address 4-word block size. Each word was 32-bit or 4 byte. Each block was 4 word. So for each of them, I needed 4 byte, so 16 byte. And for addressing 16 byte, I need to have 4 bit to address those 16 bytes because I have to understand which byte is it, right? Byte 0 to byte 15. How am I gonna address this? I need 4 bits. 0, 0, 0, 0 would refer to 0, 1, 1, 1, 1 would refer to 15. So in order to address 16 bytes, I need to allocate 4 bits in binary to give me a range of 0 to 15. So 64 minus 4 gives us 60 remaining for index and tag. Now, depending on the cache architecture, I need to figure out what are the indexes and what are the tags. That's all. Let's go to this. Then you have direct map, 4096 blocks. It's the log of that would require 12-bit. 60-bit remained out of 64. So minus 12 multiply the number of blocks. That would be the size. But for two-way, you need to have another bit taken because you want to address the number of sets per block. So it's going to be, instead of 496, it will be 248, right? So in order to address those, you need to take another bit out of that 12, effectively remains 11. For 4 set, you need to address 4, again with binary, you need 00011011, so 2 bits needed to address those 4-way sets. So instead of 12, now we need to take 2 more, so it's going to be 10, and a fully associative, we're going to use all the 60s because it can go anywhere. We need to address anything else. It's only one index effectively. And these are the different results: 197K, 401, 205, and 246, right? So that was for understanding index bit and offset. For multi-level cache, it's pretty easy. Just depending on the size of the cache and the hierarchy, you just have to understand the cache miss, the local or primary, or the global cache miss, taking into account both of the cases, L1, L2, or if it was L3. And you understand that by adding more cache, you're going to reduce the access time of the memory or the lower cache, because you have higher level cache first to go to L2 and then L3 and memory. So this will effectively bring up this 9 up to some other numbers closer to 1, for which it was 3.4 in this case. And we figured there's another method to understand this. Instead of going with the access time and the times we need to access that, right? We can just, with the penalty time, because 2% of the time we needed to pay the penalty, right? And 0.5% of the time we needed to pay the penalty of accessing memory. Why not find the access time of those cases? So instead of going this way, we went to the complement way. And in the case of having multiple levels of cache, there was another question from a colleague. You can easily find the global miss rate as the multiplication of all of them, like L1, L2, and L3, right? We can call it miss rate. In the case of having L3, that would be a miss rate of L1, L2, and L3, which would effectively do the miss rate of L1 multiply miss rate of L2 multiply miss rate of L3, right? That would be the global miss rate, right? That's the global. The local one is for each of them itself. Global is the overall miss rate of the whole hierarchy, right? Your L1, your L2, and perhaps your L3 goes to memory, right? So that would be the global one, because all of the so like, you don't care how many levels you have. Globally, this system fails like 1.2% of the time, right? Questions?
Yeah. So the globally is the whole thing, right?
Yes, for the whole thing. So globally, you'll understand, okay, at this global rate, I need to access memory anyways. But that doesn't mean what was the local miss rate for each of them. Yeah.
Okay.
All right, all good? Okay, I guess we've done 2021Z. We're done with that. Are you guys happy?
Yes. If we have any questions, what are we gonna do? Like,
if you're happy, just open up your camera and share your happy faces.
That will give us the bonus mark.
If you're still awake, actually. Yeah, I'm seeing some happy faces now.
So when would you actually figure out exactly the format for the exam, the final exam?
As soon as possible, I prefer to have the classical method, just like what you had in your midterm, to write and then use your cell phone and then get a photo and then submit. If we don't find a uniform and safe and fair manner for everyone, I might just switch these things to a multiple choice. Effectively, the questions would be the same. Instead of just you write everything, you just have to find a multiple choice for the answer of those. Otherwise, everything is the same.
Or maybe half multiple choice, half written.
Yeah, I'll try my best not to have multiple choice. But if eventually we went for that road, that would be the only choice. I mean, effectively, the questions are not gonna get changed much. The way you solve the questions would be just to find a multiple choice. You have to solve it yourself anyways, and then you find the answer. Yeah.
What you're saying is gonna be similar to like what we did today, right?
Yeah.
Okay.
So, for example, if we do the written one, then and we just have to send you a picture or something, right? Then do we have like the 3-hour limit, or is it like take-home exam and we just do it and send it?
I'll try to just be around 2 to 3 hours, perhaps 3 hours. Yeah.
But you have to leave room for us to upload the answers, because some of us,
Yes. I'll make sure you don't have many questions, and then I'll put aside for your potential issues that will arise. Your cell phone will be dead, your camera will be off, and your internet might be shut down. Electricity might be gone, who knows? Yeah. All right, any other questions?
No, thank you, Professor. It was a really great semester.
Yes, thank you.
Thank you. Yeah, I had pleasure to meet you all, and then talk with you, and for like 12 weeks in a row. Yeah, almost 12 weeks. And the world has gone upside down in these 12 weeks.
Oh,
You
yeah.
don't know what's going to happen in the upcoming weeks, but hopefully we'll be alive, and then you'll have to attend the final. Yeah.
Okay.
All right, guys. If there is no more questions, I'm just going to say goodbye and good night. And I'll post some announcement a week or two before the exam, so you have a clear idea of what to expect. But the questions would be similar to what we discussed. Yeah. All right.
But you said there wouldn't be any TAs this Friday, right?
No. If you had questions, you can email TAs and put me in CC. If you have problems with the grades, also you can do the same. We'll gradually upload the grades for lab M and N. So yeah.
Okay. All right.
And for the final exam, only cover chapter 4 and 5, or
yeah. But for instance, if you're asked to write an equivalent code for a C-like code, I mean, I assume you know, right, how to write a RISC-V assembly out of a simple while or for loop. So yeah, these are coming from previous chapters, but effectively the questions are around chapter 4 and 5.
How about, is possible you let us to write down the code of the RVS code, like for lab K, lab M, lab N?
I don't think I'll ask you the maximum line you write. It would be like 5 to 10. It would be like 100 or 50, right?
Similar to the midterm.
Yes.
But will we have Verilog codes, or just RISC-V?
I mean, it might be the case, but again, you've done your labs and you've been tested for your implementation. I don't want to just ask you to write so many codes. It might be like 4 to 7 lines, right?
Okay.
And I have one last question.
Yeah.
For the pipeline examples, are we gonna have any example that we haven't explained in class? So for example, we did the forwarding branch, we did the static branch. Would we have something that we've never done?
No, I mean, I'm not gonna ask you to devise a new technology at final. If you have an optimized forwarding which you haven't seen. No, the optimizations would be the same. The result might be different, right?
Yeah.
So,
right?
So you have a post like the similar example on the Moodle for chapter 4 and 5?
Yes, I've already posted it. Yeah, it's there.
Okay.
Okay. All right. No more questions?
All right, thank you.
Yeah, thank
All
you.
right.
Thank you, sir.
Thank you, guys.
Have
Have a good night.
All right, good night.
Yeah.
Thank you. Have a good night.
Too.